Hello, everybody. My name's Caitlin, and my project's going to be about infectious disease modeling. So I chose this topic because it's relevant to what's going on in the world right now with the coronavirus. And this type of application can help show how math is useful for real-world problems and how it can help us to better understand infectious diseases. It's also closely related to what I will be working on for my capstone project, so I thought it would be useful to learn. So why do we need it? Well, it's obvious that in our present day situation, differential equations can help create infectious disease models. As humans, we are always at risk of new infectious diseases mutating or forming naturally in the wild and spreading to the human population. The models also allow us to estimate the spread of the disease as well as to monitor the effectiveness of certain defense or treatment strategies. These models are inherently complicated due to the nature of infectious diseases. While they cannot account for each individual contact that may occur, they take the main variables into consideration to create the most robust models possible for disease control. So this is going to be called the SIR model. This is the standard base for many infectious disease models. With this model, we have an independent variable time t in days, and there will be two sets of dependent variables. The first set given below is just the generic, so the s is going to be, they're all functions with respect to time. So we've got s of t equal to the number of susceptible individuals. I of t is the number of infected individuals, and then r of t is going to be the number of recovered individuals. So the second set of dependent variables is similar, except that it's going to be more of a proportion. So what we do is we take all of the above variables and then we divide it by the total population n to obtain the portion of the population that falls into each category. So we denote this with just lowercase versions of all of the functions. That'll be big S of t divided by n is going to be the susceptible portion of the population. Big I of t divided by n is the infected portion of the population. And then big R of t divided by n is going to be the recovered portion of the population. So you don't need both sets of these. Either one will produce the same correct result. But there will be times when you will want to use the proportions because it'll allow for easier calculations. It's important to note that these models assume a fixed population, so they do not account for births or deaths or immigration if you're looking at a disease that's contained in a certain defined region. Then they don't account for any of like immigration in and out of that area either. It's also important to know that they consider recovered individuals to be immune and are no longer able to be infected. So here we have the different categories and their differential equations that we've created. So the first one is going to be the susceptible equation, which is going to be ds over dt is equal to negative b s of t I of t. The infected equation is di over dt equal to b s of t times I of t minus k times I of t. And then our recovered equation is going to be dr dt is equal to k it. So in these, b is going to be a fixed number of contacts per day to the susceptible individuals, which is how the disease will spread. And then k is a fixed fraction of infected individuals that will recover on some given day, depending on how long it takes how long the disease is infecting the person for. Off to the right here, we do have a graph. This is just a general graph. It was just from online of a general solution curve for this type of model. So what you see here is the slope is 0 at our maximum number of infected people. And then that's actually created when our rate of people recovering is equal to the rate of people becoming infected. And so that's how you see here in the infected equation. We've got this rate here, which is our rate of people becoming infected, minus the rate here of people who are recovering. So when that is 0, then our slope here is going to be 0. So how do we solve them? So first let s equal s of t, I equal I of t, and r equal r of t, just to sort of simplify our equations that we get into down here. So we can rearrange these equations from the previous slide so that we actually do like what we do in class where we separate the variables some. So we're going to get d of t on the right-hand side of these equations. And then as you see here, we've got those. I'm not going to read them all out. It's a lot of variables. So we're actually going to use Euler's method to solve these equations. We can use this method to derive 3 solution formulas for each of the above differential equations. By applying the concept of Euler's method, we obtain these formulas here. Also a long thing, but essentially S sub I is the day that you start with, and then S sub I plus 1 is going to be the next day and the next day after that, and so on and so forth, and it'll just be an iterative number. So the next step, though, is we want to actually isolate our S sub I plus 1, I sub I plus 1, and R sub I plus 1 from the S sub I sub I, and R sub I values. So we're going to essentially just move these values over to the other side of the equation. And of course, to do this, we're going to add them, for each of their own equations over to the right-hand side. So then in the end, our final form of the solution equations are going to look like these 3 down here on the bottom, where we have separated all of our sub I plus 1 variables from the just sub I variables. So in order to use Euler's method for these models, we need definitive values for B and K, as well as initial values for S of 0, I of 0, and R of 0, and then dt. So we're going to go through an example where the model has a time step of 1 day, meaning it's only updating the model on a daily basis. Let's say that the B, which is our rate of contact with susceptible individuals, is 0.7, and then we're going to say that our K, which is our time it takes for these infected individuals to recover, that is going to be 0.125 because we're going to just say it takes them 8 days to recover. So that number K there is always going to be found with just 1 over the number of days that it takes for the individuals to recover from the disease. All of these values that we're giving here in this slide are just, initial values that we chose to do an example. It could be anything. You could start with any number of days it takes to recover and any number for the rate of the contact with susceptible individuals. We're just, choosing some here to do an example with. So then we just need now to do the rest of our initial values. So our total population is going to be equal to 1. So that's just, 100% of the population. We're just calling that 1. And then our initial infected value at time 0, let's just say that it's 1/10 of 5% of the population. It seems like a strange number, but we're essentially just saying that we're starting with a very small number of the population that's infected. So when you do that math out there, you're just going to get 0.005. And then for our R of 0, this is the recovered amount at time 0. We don't have anybody who's recovered yet because it's time 0. So everybody is either susceptible or there's a very, very small percentage of the population that's infected to start with. And then no one has recovered yet. For our S of 0, we're actually just going to do 1, which is our population, minus the percentage of the population that's infected to get our susceptible proportion of the population, which is going to be this 0.995. So these can be done by hand if you're practicing with a small number of days observed, but realistically an application like this would run on a computer program because typically they're observing over a large number of days. So here we actually did it in a computer program, and this is just an Euler's method table essentially. So to fill in this table appropriately, you have to begin with the first row of initial values. So those were given to us. These are the S sub I, the I sub I, and the R sub I for the solution formulas that were shown earlier, where I sub I is the day. So we're going to start with day 0 here. And then again, we were given that on day 0, our infected portion of the population was 0.005. And then we don't have anyone recovered yet, so we've got a 0 here. And then for this, it was the 1 minus the percentage of the population that was infected. So we've got 0.995. Off over here to the right, these were given to us also in the initial statement. So we have a dt of 1 because we are only increasing by 1 day every time we do our iterative process. We've got our b, which is 0.7, that was given. That's the rate of contact with susceptible individuals. And then we've got our k, which is the rate of recovered individuals. So once we've got all of that, actually, we can sort of just create this second row here with the formulas that were given also a few slides ago. So what's going to happen is you're actually going to plug in the values that we have for our, this is our S sub I, this is our I sub I, and this is our R sub I. We have a dt, we have a b, and we have a k. So at this point, this box right here, this cell, is going to be our our S sub I plus 1. This will be our I sub I plus 1, and this will be our R sub I plus 1. So at this point, you actually can take all of these S sub I, R sub I, and I sub I values, the dt, the b, and the k, and you can plug them directly into the formulas for the S sub I plus 1, I sub I plus 1, and R sub I plus 1. And then you'll actually be able to just spit out values in here for you. They'll calculate it. You have to understand how to use the spreadsheet to do the equation up here. But otherwise, I mean, you're plugging in these values exactly as you see them in the formulas shown a few slides ago. Once you've done this second row here, the computer actually knows the formula now for the rest of the rows, and you're able to just click and drag and have it compute the rest of the rows for you, which is really handy, especially if you were observing, you know, a year's worth of a spread of a disease. That would be 365 days you don't want to compute by hand. So I did a 30-day model. I didn't show the whole thing here because it was very long. You wouldn't be able to fit it on one screen. But in the next slide here, I'm going to show a graph of that 30-day model. So this is the graph of the solution curve for the predicted values. So we see it's similar to the one that was shown earlier, except this one's actually based off of the data points and the initial value that we were given. So it shows that we've got roughly 56% of the population infected at some point, with the peak being around day 15 somewhat. I mean, it's not exact, or 14, sorry. And we've got the blue line here, that's our susceptible. As we expect, it starts to die down after a certain period of time because everybody has either been infected or is immune at this point. We see here the yellow line is our recovered. Again, as expected, in the beginning we don't have many recovered because there aren't many infected yet. And then as we proceed, we become, you know, a very high number of recovered from those that have been infected. And then we've got, again, our infected curve, which has a peak that will happen, and then it will start to drop off as people recover. As we see, the peak of the curve has got a 0 slope, and then we see here we've got the same things where these two slopes are going to be equal to each other, and they're going to cause this to be a 0 up here. I want to note that if our B, which is the rate of contact with susceptible individuals, if that increases, then our peak occurs at an earlier day. Same thing happens if you decrease the B, except it will be at a later day. So the rate at which people are becoming infected is highly important in these models because they determine how quickly we reach the peak of infected individuals. And often, if your rate of contact with susceptible individuals is higher, then you're actually probably going to have a higher percentage of the population that has been infected. So for the conclusion and future improvements, these models are good basic models to help understand infectious disease spreading. They can only account for so many variables and interactions, however. It's still a useful tool going forward, but as we have seen with the coronavirus, there's always more to be learned from infectious diseases and how we can mathematically model them. While this is not my own idea, as of April 2020, there has been a newer model established for more complex analysis of these models. They're able to account for individual interactions and more complicated variables. This new spatial model is called SBDIEM. It uses AI to improve the model accuracy. I couldn't find anywhere about what the actual abbreviation stands for. Ironically, it's pretty long, but since this is a fairly new model and they've just established and published about it this year because of the coronavirus, I don't know if they have, it might be like very specific terms that these represent, I'm sure. I just couldn't find the actual breakdown of it anywhere. Thank you all for listening, and this has been my project. Oh, and here are my references.